This topic is about natural logarithm. Natural log is a special function defined in this very simple manner. Imagine you have a function given by fx equals to 1 over x. Then you plot the function as a function of t. Then this is a function of f of t. Here I plot the functions in the variable of t, but I define my function to be 1 of x. Maybe I should just call this 1 of t. So imagine that you have the area under the curve starting from t equals to 1 to some values of x, where the x is any number that is larger than 0. So x could be on the right hand side of x equals to 1 or on the left hand side of x equals to 1. If x is on the left hand side of the functions, then it will be sitting on the left of 1. I'm going to define the definite integral of the function of 1 over t integrating dt from 1 to x. So here is an function defined in terms of the definite integral with the integrand function given by 1 over x. And I'll call this function f of x. This is a function, f of x is a function that is defined in the form of definite integral, where you integrate from a constant to x. We have seen this kind of function when we talk about the fundamental theorems of calculus. We define such a function, f of x, in the part 1 of fundamental theorem of calculus. So the capital function fx defined in such a way has been shown to be an antiderivative of the function f of f, where f of x is the integrand in the definite integration. If you recall the definitions of the capital function f in the first part of fundamental theorem of calculus, it is quite straightforward to realize that the derivative of the capital function fx is just equals to the derivative of the integrand function that appears inside the definite integral. So we have established this very simple relationship when you define the capital function of f of x. The function of capital F is what we call the natural log function. It has a special name which we designate as Ln. So Ln is the definition of the natural log. If x is larger than 1, then the natural log will define the area under the curve of 1 over x. If x is less than 1, then the natural log would be having a negative value. In the case where the natural log function is calculated at x less than 1, the area defined here is given by 1 over t dt from x to 1. Because x in this case is less than 1, so the area of this function must be integrated from x to 1. Then we call this the area, and the area is a number which is positive. So what I'm trying to say is that the integrations of the function 1 over t from x to 1 is positive if x is less than 1. In the case where x is less than 1, you have this number to be positive, and if you revert it, then what you get is you get dt t 1 over x with n minus sign. d dt of t x1 is equals to this. In the case where x is less than 1, then this term is positive. The integration of 1 to x negative multiplied with a negative gives you a number which is positive. Let me say it again. For the case where x is less than 1, this represents the area of the function under the curve of 1 over x a, which is positive. This term is positive if x is less than 1. Therefore, product of minus 1 and this one is giving you an positive number. What I'm trying to tell you is that the function of natural log defined as dt t from 1 to x. The values of the natural log would be positive when x is larger than 1, and the values of the natural log will be negative when x is less than 1. And what happens when x is exactly at 1? You get 0. So we have this very simple relationship that determines the sign of the natural log function. So imagine if you plot the graph of ln x, you have x equals to 1, the log function will be 0. And when x is larger than 1, then the function is positive. And when x is less than 1, the function is negative. So the function will actually look something like this. And every point on the curve, you have the values of x and x. Given any point or values of x, you can always find the values of natural log ln x. You have to remember the function of natural log at 1 is simply equals to 0. Now, once we have defined the natural log and the sign of the natural log when x is equals larger or less than 1, then we have to proceed to further investigate some of the other properties of the natural log. Next thing to explain is the domain and the range of the natural log. The domain of the natural log is obvious because by definitions, the natural log is defined for x that is larger than 0. So the domain of the functions is defined to be any number of x that is larger than 0. The range of the natural log range from negative infinity all the way up to positive infinity. That is what the slides here is saying. The next thing we want to talk about is the derivative of the natural log is just equals to 1 over x. This is a result that could be easily understood. The function we have encountered when we define the first part of the fundamental term of calculus, we have proven the derivative of the capital function x is simply the integrand function small f in the definite integration. The f of t is played by the rho 1 over t, and the a here in the definition of the natural log is 1. Here the capital function f is named as the natural log. Then you can easily recognize that the dx of ln x is just simply equals to the expressions of the integrand function 1 over x. The other thing we want to talk about is the log of x is defined for all the x that is larger than 0. Therefore, the ddx of the natural log is always positive because x is always larger than 0. So you have this very simple statement that says ddx of the natural log is always positive. And based on what we have mentioned in the previous lecture, if you have a function where the derivative is positive, it necessarily means the function f is increasing. Therefore, we come to the conclusion that the natural log function is an increasing function in x. So if you look at the natural log, you find that the graph of the natural log function, it begins from x equals to 1 at the point 0. And if you go to the right, the log function must be increasing. And it's increasing in this manner. X would never be equals to 0 for the natural log. Therefore, the functions is extending to minus infinity when it approach x equals 0. from the right. Therefore, the fact that the natural log has a derivative that is always positive means that the graph of the natural log is increasing from the left, starting from minus infinity. That looks something like this. The values of the natural log in the olden days is tabulated into a table form. You have to perform an numerical integration. Say, for example, by definitions, since by definitions, the natural log start with x equals to 1, and here is x. So the values of the natural log is just simply equals to the area under the curve of 1 over t from 1 to x. So you can perform an numerical integrations to calculate the exact value of this function, meaning that you calculate the Riemann sum of this area from 1 to x for all possible values of x. Say, for example, x equals to, say, 2.110. Then calculating the area under the curve of 1 over x from 1 to x will give you the values of the natural log for all values of x. So all the values of the natural log was tabulated in a table. When I was in my secondary school, we don't have computers, we don't have electronic calculator. We have to resort to the table of the logbook to tell us what the values of the natural log is. There is a particular values of the natural log, which is called the number e. The number e is the specific values on the natural log. When x equals to e, the values of the natural log is exactly equal to 1. So this point is given by the statement that the natural log value at the point where x equals to e is exactly equals to 1. You have to remember two things up to this point. You have to make sure that you are familiar with the shape of the natural log, and you have to be familiar with the fact that the values of natural log at x equals to 1 is 0, and when x is equals to e, the values of the natural log is equals to 1. So this very specific value of x, where log of e is defined as 1, is called the Euler number. The Euler number is an irrational number, and it cannot be expressed as a ratio of two integers. This is a graph that shows the values of e, and the decimal point of e is infinity. We are going to talk about how to obtain the exact values of the Euler's number in the later part of the course. Roughly speaking, the values of e is a number that is lying somewhere between 2 to 3. So usually we express approximately the Euler number as 2.71 up to 2 decimal points. And sometimes people write the expression of E to be the ratio of 22 over 7. We are going to continue to talk about more properties about the natural log. The derivative of the natural log is 1 over x by definition. If you generalize this to the function of u of x, then you have these results.